In this video, we'll talk about the Diels-Alder reaction. We'll talk about first different aspects of the Diels-Alder reaction, different kinds of dienes and dienophiles that participate in the Diels-Alder reaction, and then we'll talk briefly about the stereochemistry of the Diels-Alder reaction. Diels-Alder reaction is pretty much the only interesting reaction of conjugated alkenes, two conjugated alkenes that we'll talk about. Then as we increase conjugation, we'll get into more interesting reactions. Okay, so what is the Diels-Alder reaction? Well, we typically think of it as a reaction between a diene, meaning two alkenes that are conjugated, so it's going to be a conjugated diene with a single alkene, which is usually called the dienophile because it reacts with a diene, so we'll call this the dienophile. Notice that this carbon is going to become bonded to this carbon, and this carbon is going to become bonded to this carbon, and the double bonds shift over. So what happens is we lose 2 pi bonds in our reactants. We have 3 pi bonds here, but we only have 1 pi bond, and we gain 2 sigma bonds. So this is a exothermic reaction because we're breaking weak bonds and forming strong bonds. But notice, even though it's an exothermic reaction, right, it still takes 200 degrees and high pressure to react butadiene with ethylene to make cyclohexene, and the yield is pretty low. So this is a crappy Diels-Alder reaction. One way to improve the Diels-Alder reaction is to attach an electron withdrawing group to your dienophile. So in this case, we have an aldehyde. It has an electronegative oxygen atom, which is pulling electrons out of this dienophile, which makes it more reactive, which means that this reaction can proceed much more readily and give us a much better yield of our product. So we'll talk about that more on a future slide. Okay, so what's the mechanism of the Diels-Alder reaction? It's actually pretty easy to draw. If we take the first example on the previous slide, this happens in one step. The Diels-Alder reaction happens in a single step. So what must happen is that this pi bond breaks and becomes a sigma bond between these two carbons. This pi bond becomes a pi bond between these two carbons, right, because we have a pi bond here. And this pi bond becomes a sigma bond between these two carbons. So we have 3 arrows that are all occurring simultaneously. You can draw this going clockwise or counterclockwise. It'll give you the same answer, right? So let me show you the counterclockwise version on the second example that we showed. So let's say we had this reaction. If we drew the arrows in this direction, we would get the same outcome, same product. We're forming this bond, and we're forming this bond, and we're forming this pi bond. Okay, so let's look at a potential energy diagram of this reaction. We start with our diene and our dienophile. They start to get close to one another. These bonds start forming, right? That's what these dashed lines mean. We're going up, 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 up in energy. We hit our transition state, and then we drop back down to our product, which is more stable than our reactant. This is a single step, so we have one hump. We have 3 arrows where the dienophile is being attacked by the diene, and at the same time the dienophile is attacking the diene, and this double bond is moving over. Pretty straightforward stuff. Okay, so what's not super straightforward is taking what we've learned in the previous video about molecular orbital theory and applying it to understanding how the Diels-Alder reaction works, right? So remember in the last video that if you have butadiene, right, it has 4 electrons, and it has this orbital which has 2 electrons in it, and then its highest occupied molecular orbital has 2 electrons in it, and it doesn't have any electrons in its lowest unoccupied molecular orbital. If you take just a carbon-carbon double bond, right, there's only 2 electrons. Those are in the highest occupied molecular orbital, the pi bond. The pi star is the lowest unoccupied molecular orbital. The antibonding pi orbital doesn't have any electrons in it, right? So what's happening in the Diels-Alder reaction? Well, what's happening is we said that what we generally do is we take a Dienophile and we put an electron withdrawing group on it. If you put an electron withdrawing group on a Dienophile, what it does is it lowers the energy of the Dienophile, so it drops down in energy like that. See, this is ethylene. This is ethylene with an electron withdrawing group. And now what happened is that these electrons in the highest occupied molecular orbital of butadiene are pretty close in energy to this empty orbital. And so electrons can funnel from a full orbital to an empty orbital. And on the next video, I'll show you how those orbitals line up with one another. Okay, so if we go back here, right, notice that the two ends of our highest occupied molecular orbital are out of phase with one another. So you have red down and red up here. And the two ends of our lowest unoccupied molecular orbital for ethylene are also out of phase. And so these things can line up perfectly. On the next slide, we'll see that you have the highest occupied molecular orbital can match up with this red lobe, and this red lobe can match up, and this blue lobe and this blue lobe can match up. And so this can form a sigma bond, this can form a sigma bond, and we get this new sigma bond here and this new sigma bond here, which is the two new bonds that we form in our Diels-Alder reaction. Okay, so what are some common dienophiles that you'll see? Well, the most common electron withdrawing groups that are used to make dienophiles more reactive are things that contain carbon-oxygen double bonds, like a ketone or an aldehyde, an ester, carboxylic acid, or in this case a nitrile. These things will all pull electrons away from our dienophile, which will make it more reactive. What's important to note here is the stereochemistry of the dienophile is preserved in the Diels-Alder reaction. That's really important. So we'll say stereochemistry is preserved. So what does that mean? That means if you have a cis alkene, right? So if these are electron withdrawing groups, whatever X is, then they're going to be cis to each other in the product. So if you start with a cis alkene, we get a cis cyclohexene. And if they're trans to one another, we're going to get a trans cyclohexene, okay? So let's look at an example of this. So when you're drawing the product here, right, you want to show, since these two things are cis to one another, you want to make sure that you show them cis to one another in the product. They could be both up, or they can be both down, and actually you get both products. These are a racemic mixture of each other, but you want to be sure that if you start with cis, you draw the cis product. Alternatively, right, if we started with a trans alkene, then you want to make sure that you draw the trans product where one nitrile is down and one nitrile is up. Okay, so now we've talked about the dienophile. Now let's talk about the diene, right? We know that single bonds can freely rotate, right? So this thing is constantly spinning around, right? And so we call these two conformations of the diene the S-cis, which just means that single bond is in the cis conformation, or what we've called previously the eclipsed conformation, or this would be this anti-conformation, or the S-trans, right? This is the only one that can react in a Diels-Alder reaction, right? Because those two ends have to simultaneously react with the two carbons of the dienophile, right? So the S-trans conformation is unreactive. So even though you have a conjugated diene here, it's locked in the S-trans conformation, so it will never do a Diels-Alder reaction. Okay. Other things about the diene is that it likes to have electron-rich components to it. So one really common diene is cyclopentadiene, right? Because it's locked. Not only is it locked in the S-cis conformation, it also has a CH2 here, which is alkyl groups are electron donating, which also helps. So this is probably the most confusing part of the Diels-Alder reaction, so don't let this confuse you too much. If you imagine cyclopentadiene as flat, right, and this finger is the CH2 right here, right, as the dienophile comes in underneath, it pushes that CH2 up into a bridged compound, right? So if you have your dienophile that's coming in, right, underneath, it's going to push this group up as it forms a bond here, and as it forms a bond here, you're going to push this group up to get what's called a bridged bicyclic system. Another way to draw this, which is less confusing for a lot of people, let's say we have cyclopentadiene. Oops. We have cyclopentadiene reacting with a dienophile. Let's just say ethylene, right? We're forming a new bond between those two carbons. This guy's moving over. We're forming a bond between those two carbons. So just draw the new six-membered ring that you formed, right? And then if we number carbons 1, 2, 3, 4, 5, 6, and we call this 7. This was 1 bonded to 2, 2's bonded to 3, 4, 5 bonded to 6, right? But notice 2 is also bonded to 7, so we have 7 here. And then 7's also bonded to 5. So you could this is a similar way to show this, but it's not on the same three-dimensional perspective. So this is okay. All right. The last thing we're going to talk about in relationship to the Diels-Alder reaction is the Endo Rule. This is also kind of tricky to think about, and this is when it's helpful to draw these things in three-dimensional perspective, right? If you have cyclopentadiene and you have a cis alkene, right, we can have at least theoretically two possible products, two isomers. We could have the things cis to each other, and the bridgehead could be up, right? So we could have CHO down, and this CH2 could be sticking out of the page, or we can have this group up, and we could have the aldehyde up and the aldehyde up. This product is called the Endo product, and this is called the Exo product, right? Turns out that the Endo product is always favored for reasons that we'll show on the next slide. So you want to remember, Endo is always favored in the Diels-Alder reaction as far as we're concerned. And Endo just means that if the bridging carbon is sticking up, then the other groups are sticking down. Endo is opposite. Exo means that they're both sticking up. Endo product is going to be favored. So let's look at why. I'm not really worried about you knowing why, but I think it's interesting that from a molecular orbital perspective, right, the Endo product is favored when these two groups kind of fold in underneath the ring. So this group is down, and when we kind of unravel it, we get this Endo product here, and that is because these pi bonds are overlapping with these pi bonds in the transition state and lowering the energy of the transition state. If we look at the Exo product, these pi bonds are not stacked underneath these pi bonds, so we're not stabilizing the transition state. So the transition state's higher in energy, which means it's formed slowly. So if we put all this together on the next slide, right, we have a lowering of energy of the transition state in the Endo product, even though it's kinetically favorable, it's actually thermodynamically unfavorable. It's a little bit higher in energy. But since there's not stabilization of the transition state in the Exo product, it forms more slowly, right? We have a higher activation energy. Okay, so to summarize, what do you need to know about the Diels-Alder reaction? Well, it takes place between an electron-rich diene and an electron-poor dienophile. It makes a cyclohexene. You need to be able to show the product of any Diels-Alder reactions. You want to know, in terms of stereochemistry, you want to know cis dienophiles give cis products, trans dienophiles give trans product. In terms of the stereochemistry of Endo versus Exo, Endo is always favored. and practice this as much as possible in order to really dial in how to quickly draw the products of a Diels-Alder reaction.